Looking at problems 6 through 9 on our energy review paper. Number 6, you are getting ready to play the game of pinball. You prepare to launch the ball into play by pulling back on a spring on which the ball is resting. If you exert 8 newtons of force to pull the spring back 0.05 meters, what is the current amount of potential energy possessed by the spring? So we're looking for spring energy here. Now the equation for spring energy, if we jump over to the end of the problem, is 1/2 kx squared, where k is what's called the spring constant. X is the amount that the spring is squished or stretched. In this case, it's stretched. But the issue here is we don't have K. We were given a force of 8 newtons, but we do not have the K value, the spring constant. So we have to use Hooke's law. Force of a spring equals the spring constant K times how much it was stretched in order to find out the K. We have the force that it took to stretch the spring. That was the 8 newtons here. And the X was how far it was stretched, the 0.05 meters or 5 centimeters. Solving for K, I'm just going to divide my X over to the other side, so I get force of the spring divided by X equals K. Force of the spring is 8 newtons, X is 0.05 meters. That gives me a spring constant of 106 newtons to stretch this spring 1 meter. That's how much force it takes to stretch the spring 1 meter. Plugging that K value in my potential energy section here. Potential energy is 1/2. K value we just solved for, 160 newtons per meter, and the X is 0.05 meters. Don't forget to square it. When I plug all that in, I get a potential energy of, with my spring, of 0.2 joules. Number 7, a 75 kilogram skier rides a 2,830 meter long lift to the top of a mountain. The lift makes an angle of 14.6 degrees with the horizontal. What is the change in the skier's gravitational potential energy? We're looking for PE for gravity. Well, the potential energy with gravity is the equation mgh. We have the mass, we have the g is 9.8, we don't have the h, so we got to solve for that. We know the ski lift is 2,830 meters long. We know the angle, that's down here, 14.6 degrees. We need to solve for h, a little right triangle geometry. And because it's the opposite side of this angle on our right triangle, we're going to be using sine. So the sine of the angle equals the opposite, h over the hypotenuse, 2830 meters. Solving for h, I just have to multiply 2,830 meters over to the other side. So when I multiply sine of 14.6 degrees times 2,830 meters, I get a height change of 713.36 meters. Now I can plug into my potential energy equation. M was given in the problem at 75 kilograms. G on Earth is always 9.8 meters per second squared, and the height we just solved for at 713.36 meters. Plug all that in, and you have a potential energy change of 524,320 joules. Number 8. Now we're into work problems. A force of 825 newtons is needed to push a car across a lot. 2 students pushed the car a total of 35 meters. How much work did they do? Well, in our work equation, it's force times cosine theta d. Well, the cosine theta part is the angle between the direction of the force and the direction of the movement. But if you're pushing the car to the side and the car is moving to the side, the angle between them is nothing. It's just 0, which is why I have theta equals 0. And the cosine of 0 just equals 1. So we can, when there's no angle, we can just ignore it entirely and turn our equation into work equals force times distance. The force was given at 825 newtons, the distance was 35 meters, and that gives us an amount of work done of 28,875 joules. Number 9. A 75 kilogram man is riding an escalator in the shopping mall. The escalator moves the man at a constant velocity from the ground level to the floor above, which is a vertical height of 4.6 meters. What is the work done on the man by gravity? Work done by gravity. And what is the amount of work done by the escalator? That's WE here, escalator. So here's our drawing. The force of the escalator pushes up. That's the normal force pushing up on the man. And force of gravity is down. If you've ever been on an escalator, you know that it does not accelerate you toward the sky. It moves you up at a constant speed, meaning that the force the escalator pushes up on you is equal to the amount that the gravity or the Earth's pull pulls down on you, your weight. So first things first, the amount of work done by gravity, well, that's the force of gravity times the distance that you move. Well, notice the force of gravity is downward and you're moving upward. They are in opposite directions. So when I plug in, my force of gravity is mass, which was 75 kilograms, G, 9.8 meters per second squared, and the distance upward was 4.6 meters. The reason why the work is downward, negative 3,381 joules, is because it's downward. The gravity is trying to take the energy away from you. When you move up, 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 your energy gets bigger because you gain potential energy, but gravity's trying to take that energy away. It's trying to pull you back down. So when you try and take energy away from an object, it's negative work. That's why it's negative 3,381 joules. Now, when it comes to the amount of work done by the escalator, well, they're equal to each other because the force of the escalator pushing up is equal to the force of gravity. So it's still 75 times 9.8. And the distance is the same at 4.6. But the work is positive because it's going upward. The escalator is giving you potential energy. It's trying to add to your energy, so you do positive work. And by the way, no change in kinetic energy means no total work done. Thus, the two works must be equal. That's a little precursor to the work energy theorem, which says the total work done on you is equal to your change in kinetic energy. Or basically, if you do total work, you have a change in speed. You don't have a change in speed. You're moving at a nice constant speed there. So there's no total work done. They have to be equal to each other, but in opposite directions, so negative and positive.